Solving these integrals requires the art of introducing the double integrals. So this is a new art that has come over in my channel, and in this video we will basically see how do we simplify these kind of integrals by changing this to double integral. Now, first of all, I will just give you the idea how do we change this to a double integral, and then after that we will also solve them, which is not a difficult task after we have the double integral. Okay, so let's see about this case. Integral from 0 to infinity of e to the power minus x square by x square plus 1 by 2 dx. Okay, so a way we can do this is, first of all, we can try to make the power also same. So basically, if I introduce a 1 by 2 over here, I can also introduce e to the power minus x square plus 1 by 2. Yeah, because this is minus 1 by 2 and plus 1 by 2 cancels out. Now after this, how I can make a double integral is, basically if here's alpha, and if I integrate with respect to alpha, this will come down. Yeah, so I will use that strategy. So what I will do is basically integral from 0 to infinity. Also I will take an integral of e to the power minus x square plus 1 by 2 times alpha d alpha dx. This will of course bring this coefficient down, minus x square plus 1 by 2 down. Yeah, and then first of what I can do is I can put the limits as 1 to infinity, because if I do that, what I will have is basically e to the power minus x square plus 1 by 2 alpha by minus x square plus 1 by 2. Yeah, now if alpha is from 1 to infinity, at infinity this is 0, and this minus and a minus over here will make it plus, and we have e to the power minus x square plus 1 by 2 alpha is 1 by x square plus 1 by 2. So this works. Yeah, so this is how we are making this change, and this is one of the important ways you introduce double integral. So basically you just notice that in the power and denominator it is same, and if you notice that, or you are able to make that, and then use this idea. So now it's a double integral, and now we can interchange the double integrals, these two, and then it will be possible to solve easily. We will do that task later on, but now let us see about the other cases. How do we do? Now how do we do in these cases? So if you try to do the same approach, yeah, if you try to introduce a plus 1 by 2 over here, yeah, and then try to take an integral to take it down, this time you might need to introduce triple integral, yeah, 2 integrals, because you have to bring it down 2 times, but that might not be convenient and easier. So there's also another way you could have introduced a double integral, which I will use in this one, and that will be used for power 3, power 4, any powers. Okay, so the way is, now we are going to use the gamma function. So basically what I will do now is, for this expression we can also introduce another integral with s as x square plus 1 by 2. So this is basically our s, and then t to the power 1 dt. We will introduce this integral because we know that if this expression was actually s, yeah, this will just be gamma of 2 by s square. Yeah, that's the Laplace transform formula, and so this expression is just gamma of 2 by s square, and we get this expression gamma of 2 is 1 and s is x square plus 1 by 2 whole square. Yeah, so now this is the double integral. We have this expression from this integral inside, and now we can interchange the integrals and solve it. So this is how we can introduce a double integral over here. Now let's look at this one. So for this one, what I can do is a similar approach. Integral from 0 to infinity, have e to the power minus x square. Now also again, integral from 0 to infinity, in place of s put this e to the power minus x square plus 1 by 2t times t square dt. Now and also sorry, and okay, and also a dx outside of this. Now we know that this just evaluates to gamma of 3 by x square plus 1 by 2 to the power 3 from the Laplace transform formula. Yeah, and we have this expression in the denominator now. Just this is somehow like unnecessary, so we divide by 1 by gamma of 3, and this is the required double integral we have. Now we can interchange the integrals, the order of integrals, and that will simplify the problem so as to be solved. So now that we have this art of introducing double integrals, now we can begin solving these problems. Let me start with the first one, and let me also make it as double integral using the new technique that we have learned through the Laplace transform formula. So for this one, it will just be integral from 0 to infinity e to the power minus x square. Again, integral from 0 to infinity e to the power minus x square plus 1 by 2 t times t to the power 0 dt, and then dx. Yeah, you know that this is just gamma of 1 by x square plus 1 by 2, so that makes sense. And then next what we can do is we can try to interchange the integrals. If we interchange these two, the order of the integrals, what we get is integral from 0 to infinity, integral from 0 to infinity, and then we have e to the power minus x square, e to the power minus x square t, and then e to the power minus t by 2 dt dx. And so because we have changed the order of integrals, now I should write it as dx dt. Yeah, dx dt. Now what's next? We will try to take constants outside the integral. We will have integral from 0 to infinity. If we take the constant outside, let's say e to the power minus t by 2 outside, we have integral from 0 to infinity. This is e to the power minus x square t plus 1, and then dx dt. Integral from 0 to infinity e to the power minus t by 2, and now we have this is just now we can use the formula from the generalized Gaussian integral, something like this. Integral from 0 to infinity of e to the power minus ax square dx, that is just 1 by 2 times root pi by a. We will use this formula, and that gives us 1 by 2 times root pi by t plus 1 dt. Yeah. Now let's take these things out. Root pi by 2 outside, that leaves us with the integral from 0 to infinity e to the power minus t by 2 t plus 1 to the power minus 1 by 2 dt. How do we deal with the things? Usually in such cases, the term where we have like fractional powers, we try to make this as a single term. So let's do that. G equals to t plus 1. That leaves us with root pi by 2 integral from 0 to infinity e to the power. Now this is minus g by 2 and plus 1 by 2. Yeah, because t is g minus 1. Yeah, and then g to the power minus 1 by 2 dg. So what do we finally have? We have root pi root e by 2 integral from 0 to infinity. Sorry, not 0. This is 1 actually. I made a mistake. This is 1, and it is e to the power minus g by 2 g to the power minus 1 by 2 dg. Okay, now what's next? Okay, so for this one, uh, we can either try to use the incomplete gamma function, or we can also take it to the error functions. Yeah, let us see how. For that, this is still not a perfect 2. 2, yeah, nice, fine. Now for that, let us first substitute, let's say alpha equals to g by 2. Yeah, that gives us root pi root e by 2, and this is 1 by 2 to infinity e to the power minus alpha, and we get alpha to the power minus 1 by 2, and then 2 to the power minus 1 by 2, and this is 2 times d alpha. So this brings root 2 outside, that gives us root pi root e by root 2, integral from 1 by 2 to infinity e to the power minus alpha to the power minus 1 by 2, yeah, and then d alpha. Okay, fine. Now what's next? Okay, now we can let like alpha equals to beta square, and that gives us root pi root e by root 2, and beta is equals to, okay, root alpha, so 1 by root 2 to infinity, and this is e to the power minus beta square, and since beta equals to alpha to the power 1 by 2, this is just beta is equals to alpha to the power 1 by 2, so d beta is equals to 1 by 2 alpha to the power minus 1 by 2 d alpha. This is actually 2 times d beta. Yeah, so we have root pi root e times, this is root 2, yeah, 2 comes outside, and now this is actually the complement error function. We know that integral from a to infinity of e to the power minus x square dx, this is just root pi by 2 times complement error function of a. Yeah, using this we have root pi by 2 times complementary error function of 1 by root 2, and this gives us the answer. So we finally get the answer, pi root e by 2 orb c of 1 by root 2, and that is the answer for this one. Let me check it. Pi root e by 2 root 2 or 1 root 2. Okay, so we did this one. This one was slightly long, but after we introduced double integral and interchanged the integrals, it wasn't complex. Just some substitutions on the way. But yeah, that was it. I hope you got it. Now let's go to another integrals. This one, yeah, this is also same, like, because the way we have introduced double integral is same, the solution will also be almost same, but let me just do it. If any of you are stuck on the way, you might want to watch the solution, so that's why let me still do it. If you know, even though you now have the idea how to do, I'm going to solve this one. Yeah. Okay, so from what I have told you earlier, this will just be integral from 0 to infinity e to the power minus x square. Again, integral from 0 to infinity of e to the power minus x square plus 1 by 2 t, and then t to the power 1 dt dx. Yeah. So now what's next? Okay, so of course the next step is to interchange the integrals after take the constant outside. So integral from 0 to infinity, integral from 0 to infinity e to the power minus x square, e to the power minus x square t, e to the power minus t by 2 t, yeah, yeah, and then dx dt. Now we can take the constant outside the integral, 0 to infinity. Basically e to the power minus t by 2 and t are the constant. Integral from 0 to infinity Over here also we have e to the power minus x square t plus 1 and then dx dt. What can we do next? Sorry. So now what next can you do? You know the approach, yeah, we did earlier. 0 to infinity e to the power minus t by 2 plus, oh no, this is not plus, this is t. And now here it is, we know that it is 1 by just root 1 by 2 root under pi by t plus 1 dt. Now next is to take this root pi by 2 outside. 0 to infinity e to the power minus t by 2 and then t plus 1 to the power minus 1 by 2 and then dt. And okay, I think I forgot a t over here. Yeah. Next step, let this as g as t plus 1. So you have root pi by 2 and the integral going from 1 to infinity. T is just g minus 1 and then you have t as g minus 1, so you have root e over here and then you have minus g by 2 over here and then g to the power minus 1 by 2 dg. What's next? Okay, so this time we earlier didn't have a variable over here, just the number we had, but now we also have a variable. Yeah, and that might make our work slightly longer. Yeah, we have to be careful about that. G to the power 1 by 2 minus e to the power minus g by 2 g to the power minus 1 by 2 dg. Now something I want to tell you is, like, only if you have something like e to the power minus alpha to the power minus 1 by 2 d alpha integral, only in this case if you try to make substitution you will get to the case of some variable over here and then e to the power minus alpha square d alpha, something like that. Only if here's minus 1 by 2, then you can get to this case where you can either use orf of some variable or orf c of some variable, those things. And here it's 1 by 2, so you might not be able to take this to orf function. So for that you first can use the integration by parts to reduce the power of this g to the power 1 by 2. Yeah, so that's a helpful way to solve this. And yeah, okay, so what do you get? This you take g to the power 1 by 2 as u and then this as v. Yeah, and next minus integral from 1 to infinity. So this gives us 1 by 2 g to the power minus 1 by 2, and over here you get e to the minus g by 2 by minus 1 by 2. Yeah, and after that over here we have minus integral from 1 by 2, and like something really nice happens in this case though it will not happen for the power 3 or power 4 or any other powers. For other powers, like such coincidence might not happen, but for this one there's a really nice coincidence that 2 cancels out and this minus will make it plus, and you notice that these two integrals are equal in opposite. Yeah, you notice that? Do you notice that or not? Yeah, these two are the same at opposite signs, so they cancel each other out, and that's a pretty nice thing. And this is from 1 to infinity. Yeah, so you have root pi root e by 2, and at infinity this is 0 and minus, here's a minus, so that becomes plus. At 1 this is 1, this is e to the power minus 1 by 2, and this 2 comes up, so 2 times e to the power minus 1 by 2. Now this nicely cancels to just the root pi. This is the only case, and this is probably the only case where in such integrals, the generalized integral from 0 to infinity, e to the power minus x square by x square plus 1 by 2 to the power n dx. In such generalized integrals, n equals to is the only case where there is no complementary error function in the solution, and the answer is nicely root pi. But for other cases, for example for 3 or 1 or 4 or 5 or 6 or 7, there's always a complementary error function that tends to reduce the beauty of the solution. Yeah. Okay, so we have solved this, and the answer is nicely the root pi. Now I think we have done 2, and also because we started the third one as well, let's solve the third one as well. Though it's kind of long, but yeah, let's do it. And up to third one, we will end this video. Yeah. Whew. Integral from 0 to infinity, and then e to the power minus x square by x square plus 1 to the power 3 dx. Is this the problem? Is this the x square plus 1 by 2 to the power 3? X square plus 1 by 2 to the power 3. Okay, now nice. Our approach is the same. Yeah. So what do? We basically introduce a double integral, e to the power minus x square, and introduce integral from 0 to infinity, e to the power minus x square plus 1 by 2 t, and then t square dt dx. Yeah. And what's next? We try to change the integrals. 0 to infinity, 0 to infinity, e to the power minus x square, e to the power minus x square t, to the power minus 1 by 2t, and t square dx dt. Now what's next? We take the constants outside. 0 to infinity to the power minus 1 by 2t, t square integral from 0 to infinity to the power minus x square 1 plus t dt dx. Yeah. Now integral from 0 to infinity to the power minus t by 2 t square, and then this is 1 by 2 root pi by 1 plus t dt dx. Now what's next? We take these things out. Root pi by 2, 0 to infinity to the power minus t by 2 t square t plus 1 to the power minus 1 by 2, and wait, it was supposed to be dx dt, not dt dx, and so I have meshed here and also over here. Okay, so this is basically dx dt, and here's the integral evaluated, so just dt will be there and just dt will be there. Yeah. Now after this, we know that we have to let this as just the g, so we have root pi by 2 integral from 0 to infinity. We get a root e over here, and e to the power we get e to the power minus g by 2, and this is g minus 1 whole square, and g to the power minus 1 by 2, and then dg. Yeah, so basically made substitution g equals to t plus 1. Now after this, I think just evaluate evaluate the square, and then you will get multiple expressions. Try to use integration by parts in the first one, and something will reduce to value, and the next one will add up to the third one. Again, evaluate the integral, and there will be some values over here, and the next integral will add up to the another one. Again, at last you will have some integral with g to the power minus 1 by 2 only, where you can basically use the r function, and this is how we will solve this integral. Like it is my computer isn't really responding well to my touches, and I will just let you know the answer over here. I think it's not worth it to solve in this way. So we have pi root e by 2 or c of 1 by root 2 plus root pi root e by 2 or c of 1 by root 2 plus root pi. So that's the answer. And you can also try for other powers, 4, 5, 6. All of them will definitely like be long, but they will definitely give the answer if you just use this approach of doing integration by parts, and the last one will simplify and you get the answer. So that was it, and I hope you have now like really got the idea of the art of introducing Taylor integrals. I hope you will use this in your like other competitions or other places as well. Hope this helps. Thanks for watching, and look forward to seeing you in the upcoming videos too.